the mass number does not equal the atomic mass. The mass number is the number of protons and neutrons in one particular isotope, and those are the more massive particles. But anytime we're dealing with a sample of an element that's large enough to see, even with a microscope, we're going to be dealing with bazillions of atoms. And they're not all going to be a single isotope unless we've taken great pains to make sure that they are. If you just go out and collect some carbon, and maybe you take water and you decompose it by passing electricity through it, and you get oxygen gas and hydrogen gas, you're going to have a mixture of all the isotopes of hydrogen and oxygen. So when we talk about the atomic mass, that's an experimental number. And it's determined from all of the naturally occurring isotopes. So what they've done is, say for carbon, they look at multiple samples of carbon and they identify what percent is carbon-12, and what percent is carbon-13, and what percent is carbon-14. They'll take a sample of carbon from somewhere else. And what's interesting is the relative percentages of the different isotopes are pretty constant over the whole Earth. So if you had a sample of carbon from, say, Sweden and one from Chile, the amounts of each of the ratios or percentages of each isotope would be pretty much the same. So what do we do to find an average of something? You add up all the individual samples and you divide by the number of samples, which is great if you're dealing with 5 numbers or 25 numbers or even 100 numbers. What if you're dealing with 10 to the 59 masses? There is not enough time in your lifetime to add those up. And you'd make mistakes anyway, right? It's just not possible, and it's not practical. So instead of a simple average, we use a weighted average. And so the weighted average allows for the fact that we don't have the equal numbers of all of the things. So we use a percentage. We take the percentage of that object. So let's say we've got 75% carbon-12. I'm drawing in the air. Nobody can see that. So if it's 75%, we can make that into a decimal. That's 0.75. So we express the percentage as a decimal. We're dividing by 100. And then we multiply it by the mass. And we do that for all the different kinds of things that we have. And we add those up and we get an average without having to look at each individual thing. So when we talk about a percent natural abundance, that means the relative amount found in a sample. I don't remember why I left so much blank space. There was probably a reason, but not necessarily. Anyway. Oh, look at that. Animation slipped in there. I don't like animations anymore. I used to like them, but I don't like them anymore. Okay, so here, this is why there was the blank space. So here's a neon sign. Memphis sounds, cool jazz, hot blues. It is orange light. What kind of a sign is this? It's a neon sign. Do you know that neon signs actually contain neon? A neon sign is a tube, usually glass, containing a gas, such as neon. The orange light is from neon, and you pass electricity through it, and it causes the gas to glow orange. So in these tubes is neon. If we were to look at the neon atoms and say, okay, here's a sample of these neon atoms, neon has 3 different isotopes. There's neon 21, neon 22, and neon 20. They differ in the number of neutrons, but all of them have the same number of protons. So 0.27% of all the atoms in there are the neon 21. 9.25% are the neon 22, and most of them are neon 20. And we can calculate the average using these percentages. Because when we deal with a sample of matter, we're dealing with a whole bunch of atoms. And so we want the average mass. We don't care that some weigh a little more and some weigh less. We want an average. So let's look at how we would do that. We use the weighted average because we don't have equal numbers of each of them. So we'll look at copper. 2 isotopes of copper, copper 63, copper 65. This one has a mass of 62.930 atomic mass units. And there's something that also has just gotten sprung on you. Have you heard of atomic mass units yet? No. So atomic mass unit is a unit that we made up to measure the mass of an atom. Very creative name. Atomic mass unit, a unit that measures the mass of an atom, right? And does it disturb anyone that we made up a unit? That sounds a little flippant, doesn't it? We just made up a unit because it was convenient. Where did all units come from? We made them up. It's just that some of them were made up so long ago that we think they've always existed, right? Nobody has problem with the unit foot as a length. You know where that came from? It was the length of the king's foot. It's a foot long, right? It's great for approximating things. You can just pace it off. You've got this measuring device at the bottom of your foot. Bottom of your leg. Hopefully you don't have a foot at the bottom of your foot. That would make purchasing shoes difficult. But we've made up all units. And we need units that are similar in size to the objects that we're measuring. Okay, so I live in Reedley, and we would measure the distance between Fresno City College and my home in Reedley. What unit would we use? Miles. Why wouldn't we measure that in inches? We'd end up with this huge number, right? It's about 30 miles, but the number of inches would be ridiculous, right? We use a unit that is similar in size to what we're measuring. So atoms are crazy small, and so we need a unit that is on the size that they are. And so we made one up, atomic mass unit. So that's what that is. It's a unit of mass. Notice that this number is similar to the mass number, but not exactly the same. We said the relative masses were 1 atomic mass unit of each, the proton and the neutron. That's an approximate number. This is a little more exact. So it's close to 63, but not exactly. So 69.09% of all copper is copper 63. And then there's copper 65, which has this mass, 30.91%. The percentages are always going to add up to 100. And so to find the average, we're going to take the percentage, we're going to divide it by 100 to make it into a decimal, and multiply it by the mass. And then we're going to add that to the other percentage made into a decimal, multiplied by the mass. And you do that if there's more than 2. You just keep doing it until you run out of isotopes. You add them all up, and you're going to get the average atomic mass. Now, just like when you take the average of 2 and 3, what's the average of 2 and 3? 2 plus 3 divided by 2 is 2.5, right? It's between. The average has to be between the highest and lowest numbers. So if you're doing this math and you come up with 72 atomic mass units, you did something wrong. It happens. Try again. Write out what you do. An important skill that will help you to be successful when you get to 1A is learning to show your work. It seems tedious sometimes, but it can actually save you time in the long run. So write it out. Do it on your calculator. Write down the answer. Do it on your calculator again. I don't know about you, but I make mistakes all the time when I'm punching numbers into my calculator, right? Sometimes you catch them, sometimes you don't. So I like to play a little game with my calculations, and it's best 2 out of 3. So I do the calculation, I write down the answer. I do the calculation again. If I get the same number, I probably did it right, or I'm really good at making the same mistake. If I get a different number, I'm going to do it a third time and go for best 2 out of 3, okay? And that can save you points on an exam. It doesn't take that long, maybe 5 seconds to do the calculation again. So let's do this. If silver is 51.84%, silver 107, with a mass of that, and the rest is silver 109, with this mass, calculate silver's atomic mass. So we want the average. So what we're going to do is we're going to take this percentage and divide by 100. So we're going to get 0.5184, and we're going to multiply that by the mass of that isotope, 106.9051 AMUs. We pronounce that abbreviation AMU, not AMU. AMU might be some distant relative of an emu. The rest is this. They didn't give us a percentage. What do we do? Well, the total has to be a 100%, right? So we take 100 and we subtract 51.84, so that's 48.16%. That's this guy, the rest. So 0.4816, that's a really bad period. There we go. It times the mass of that one, 108.9048. I ran out of room, AMU. Now, one of the things that trips students up is your calculator. They make far too many different kinds of calculators, if you ask me. You need to learn how your calculator works and how to communicate with it so that you can come up with the correct answer reliably. Okay, that's why it's important that you have your own calculator, and you should bring it to class every time. Some days we won't use it, but a lot of times we will, and I encourage you to type along on your calculator and check me, because I make mistakes, and it's so much fun to catch a teacher making a stupid mistake on the calculator, right? So go for it. So I'm going to do 0.5184 times 106.9051 plus 0.4816 times 108.9048 and press equals. Your calculator should understand the order of operations for this. And so my calculator is showing me this. And the unit would be atomic mass units. Is that how we should report the answer? No. Did you have a question? Oh, about the Sig Figs? So I don't know what Dr. Umber, what his policy is. What I recommend is write everything down that your calculator gives you, even recognizing that a lot of it's garbage. This stuff at the end, most of that's just garbage. Write it down, because if you write down too few digits, the only way to find out the correct answer is to do the calculation over again. If you write down too many digits, you can always go back and chop some off later. So how would we find the Sig Figs with this one? This is one of those tricky ones where we've got multiplying and adding together. So what we have to do is we have to look at the result of this and the result of that and then look at the addition. So the first part, 5184 times 106.9051. I'm going to change color because this is just us thinking about the Sig Figs. Sig Figs are a big deal in Chem 1A. That's what my calculator shows me, is the result of this multiplication. What's the rule for multiplying? Whichever number has the fewest number of significant figures. So that's this one, right? How many Sig Figs? 4. So then this number should have 4 Sig Figs. So that would be the 5, the 5, the 4, and the 1. 4 Sig Figs. The uncertain digit is in the second decimal place. When we're doing the math, we don't want to round that off because we'll introduce rounding errors. But we're going to go back and look at what was going on here. So 0.4816 times 108.9048. Did you get that right? And I'll write this one up here. 52.44855.168. How many Sig Figs should that number have? 4, because again, we've got 4 here. This one has more. It's the smallest number of Sig Figs when you're talking about multiplication and division. So this one has 4 Sig Figs. Now, when we're adding, we're concerned with decimal places, right? So if we stack these up to add them, we're going to get that result that the calculator gave us. But where's the uncertainty? In the second decimal place. So there's different ways to think about this. The rule says you look at the number with the fewest decimal places. Here they both have 2, and so we'd say, well, this one's going to have 2. Another way is you can stack them up like this and then draw a vertical line to the right of the last Sig Fig. And so that tells you where to stop. So we should report this as 107 point, what? 87. We need to round that up. And there's our result. That has 5 Sig Figs. None of the numbers we started with had 5 Sig Figs. That happens when you're mixing multiplication and division. Now in this class, we generally don't combine things a lot. So on an exam, I will probably end up writing your exam for next week. I'm not going to try to trick you. Okay, so if you think, ooh, there's a trick question, probably not. I would not ask you a question about calculating atomic mass and then give you this and this guy as 2 answers, making sure that you knew Sig Figs. I wouldn't do that. I'll test you on the Sig Figs separately. Okay, but you should practice using your significant figures always. Any questions? Do you want to do another example, or are you good? One more? Never hurts. Okay, so here we've got boron. Boron rhymes with moron. Poor boron. 19.9% boron 10, 80.1% boron 11. Now this one is saying, calculate the atomic mass of boron, report it to 2 decimal places. And sometimes mastering chemistry does that. It'll just flat out tell you, this is how many Sig Figs, or this is how many decimal places. And then you don't have to worry about it so much. What did I do? I pushed on something. That happens. Okay. So what are we going to do? We're going to take the percentages, change them into fractions. So 19.9 becomes 0. Oh, I don't want to use red. Red is the teacher color. Purple's friendlier. 0.199 times the mass of that isotope. 10.013 AMUs. Plus, changing 80%, we get 0.801. Be careful when you get one that's like 5%. Sometimes students write down 0.5, but that's 50%. Be careful with your percentages here. So 80%, 0.801 times 11.009 AMUs. And then get out your calculator. If you write it down and you've made a mistake, you can actually look back at what you did and figure out what went wrong. If you don't write it down, then you have to start over. Okay, so obviously I did something wrong. My calculator is showing me this. Could that possibly be the right answer? No. The average has to be between 10.013 and 11.009. So obviously I did something wrong. Okay, that's not right. So I'm going to go back and do it again. 0.199. Now, I probably didn't hit a decimal, or who knows what I did. Okay, so this is looking better. 10.810796 AMUs. Anybody else get that number? Yeah. So we'll call you the second time through on the calculator. Well, the third, right, because I screwed up in the first. How should we report the final answer there? 10.81. It says 2 decimal places, so we're going to do 2 decimal places. We're going to follow the direction. Any questions? On the periodic table, what's the number under boron? 10.81. Huh. You think that's a coincidence? No. That's another way to check your work. So if you're actually dealing with a real element, you can check your answer with the one on the periodic table. Now, the atomic masses on periodic tables vary a little bit. Okay, so don't be disturbed if you see one that's just slightly different. But what we do on exams, because we know you can look up the mass on the periodic table, is we'll make up an element that's not on the periodic table. You want to do this one? This one's got more. It's got, what, 3 of them? Same idea. Oh, there's another one. Bromine. Oh, this one's different. We need to do this one. So this is a tricky one. It says bromine has 2 naturally occurring isotopes. Bromine 79 and bromine 81. Has an atomic mass of 79.904 atomic mass units. The mass of bromine 81 is 80.9163, and its natural abundance is 49.31%. What's the mass and natural abundance of bromine 79? This is different than what we were doing before, isn't it? One of the hard things, this is a word problem, isn't it? When I was growing up, we called them story problems. Doesn't that sound nicer? Oh, it's a story problem. We get to hear a story. Except all the stories are really boring, aren't they? The hard thing about word problems is translating that into a mathematical equation. If I gave you the math equation, that would be much easier to deal with. But sadly, chemistry and life are full of word problems, and so we have to learn how to decipher them. One approach, always read through the problem all the way to the end, even if it's boring. And then go back and look at those numbers. The numbers are generally important. So let's go back and look at these and see what they are. So we've got we've got two isotopes. We've got bromine 79 and bromine 81. So let's write those guys down. There's bromine 79 and bromine 81. And it says bromine has an atomic mass of 79.904. Is that the mass of one of these? It's the average mass of both of them, right? So the atomic mass of bromine equals 79.904 AMUs. So we took care of that number. The mass of bromine 81 is this. Okay, so that pertains to this one. So this one has a mass of 80.9163 AMUs. And its natural abundance is 49.31%. So do you see these, bromine 81, this mass, this abundance, all go together. So there we basically covered all the numbers. And then we always need to know, what are we trying to find out? Because sometimes you can do a beautiful, elaborate calculation, but it wasn't what the problem asked you to do, so then you don't get credit for it. It might have been wonderful, but nobody cares. What do they want? The mass and abundance of this guy. So mass, percent, that's what we want to know. This problem is, I think, one of the most difficult problems that shows up in this class. And I really question why they even put it in this class, but it's in there. You'll see it on the worksheet. So we need to do it. We have two things that we're trying to figure out. So what relationships do we know?
Well, we have the natural abundance of one of them. We can subtract that from 100 is the natural abundance.
Yes. We know that the percent abundances have to add up to 100. So let's put some variables in here, because the reason mathematicians use variables is it's so much easier than writing out all these words, right? So let's call this percent, what should we call it? X?
Yeah.
We'll call that X. And what should we call this? Oops. Did I do that? No, I didn't. Okay. I wanted to do this. What should we call the mass? Ooh, how about M? Okay. So we're going to call the mass M, and we're going to call that percentage X. So I'm going to kind of, I'll use the top later. So I'm going to switch colors here just because maybe it'll be a little clearer. So we know that these percentages, we know that 49.31% plus X percent has to equal 100%. So can we figure out what X is? Yeah, we can. So X equals 100 minus 49.31. So that, wow, that was really ugly. It must be getting late. 51.69? 50, yeah. I knew that. 50.69. Okay, so there we got one of them. How do we figure out the mass?
Figure out the 49.31 times 80.9.
So basically what we're going to do is we're going to pretend that we're solving for the atomic mass like we did before, except now we know the atomic mass and we have this variable that we're going to stick in there. But we can use the same form of the equation. That's what you meant, right? Mm-hmm. So we'll do that. We'll take this 49.3%, we'll turn that into 49.31, times the atomic mass of that guy plus this percent that we just figured out, 0.5069, times the mass of that one, which we're going to call M, and that is going to equal this atomic mass, 79.904 atomic mass units. Then we have to solve for M. There's different ways to think about that. Some of you can just do it in one big step on your calculator, and others of you need to do it in pieces. I'm going to do it in pieces for you. So I'm going to take those first two numbers, 0.49, can't read my own writing, 4931 times 80.9163. So this part is 39.8998. So it gets a little tedious writing everything down. Usually if you write down 2 extra digits, it'll be good enough. So this product here should have how many sig figs? 4. So 4 would be right here. So 8998, that's 2 extras, that's good enough to avoid problems with rounding. Plus 0.5069 times M equals this. We need to have M on one side and all the numbers on the other side. There's algebra and chemistry. Some of you don't like algebra. We only use little bits of algebra, and so if you're rusty on algebra, please ask me, and I can explain it to you. It's really not that bad. So what we want to do here is we want to move this to the other side, and we'll do that by subtracting it from both sides. So we'll take 39.8998 minus 39.8998. That equals 0. So then we'll end up with 0.5069 M on this side. Let's see here. This line is in the way. It's pretty and everything, but and those guys, some of those words are in the way too. I really got the iPad so I could color while I'm working. It's fun. Okay, I'll stop. So we're going to end up with 0.5069 M is equal to, I'm going to do this math here. I'm going to take the 79.904 minus 39.8998. And my calculator is giving me 40.0042. Let's keep track of the sig figs because it's easier to keep track of them as you're doing this rather than to try to go back later. So we're subtracting this number with 2 decimal places from this number that has 3. So that means that this number can only have 2 decimal places. So I'm going to underline that. That's the last significant figure. I'm going to let the 4 and the 2 hang around so I don't get a rounding error. How do I get the M by itself? Divide by what it's multiplied by. So I'm going to divide this side by 0.5069, and I'm going to divide this side by 0.5069. The basic idea of rearranging equations is whatever you do to one side, you have to do the other. Okay, it's like Tommy and Michael. If you give one a cookie, you have to give the other one exactly the same size and kind of cookie, right? Because otherwise there's going to be trouble. So to be equal, you have to do the same thing. So we've got that 40.0042 divided by 0.5069. I need more room. And so I'm getting M is equal to 78.904 0.9193. How many sig figs should that have? This number on top has 4, and the number on the bottom has 4, so this one should have 4. So the mass is 78.92 atomic mass units. Is that a reasonable mass for bromine 79? Yeah, it's close to 79 atomic mass units. Any questions? I think this is another, I'm not going to do this one because we're all tired and want to go home, but we've got 4 minutes, and I'm going to talk about it for a second. This one gives us 2 masses of these isotopes, and it's asking for the percent abundance of one of them. Is there enough information on this slide to solve the problem? No. What we need is the atomic mass of lithium. If we knew the atomic mass of lithium, we could solve for the percentages. It'd be messy, but we could do it. Maybe we should, but I don't want to. How would we find the atomic mass of lithium? On the periodic table. So I'll just outline this real quick. What we're going to do here is we're going to say if x is the percentage of one and y is the percentage of the other, x plus y has to add up to 100. And then x is the percentage of the first one. Well, actually, what we should say is they need to add up to 1 as fractions. Plus y times the second one adds up to 6.941.
Yes.
And what you have there is 2 equations, 2 unknowns. This could show up on a worksheet. I will not do this to you on an exam. But some of you might find that fun. This one is just like it. Ta-da!